If we have an infinite charged plane, let's call it P, with a surface charge density sigma, and we are interested in computing the resultant field in any point n, a direct way is to choose some small portions, elements of surface ds, say that ds contains the charge sigma ds, and do a complicated integral is going through all the plane P, while this point A, and this would look like E created in the point M, is equal to the integral on all the plane P of sigma ds on 4 pi epsilon 0 am square times this unit vector E. This is hard to compute. So I will give here is an easy way to compute this field using Gauss Theorem and symmetries. So let's consider again the infinite plane P, and we are interested in the field created in M. First thing to see is symmetries. As the plane is infinite, it is symmetric if we consider any plane containing M orthogonal to P. It separates the infinite plane P on two regions, which are equal because the plane is uniformly charged and is infinite in this model. If we name some axes X, Y, and Z, the symmetries defined by the red plane do not allow the field to have a component directed by EY, because if it does, if it had a component going outside the plane, it would compensate itself by symmetry. That's why it's condemned to stay inside the red plane and thus be orthogonal to EY. The same thing happens if we consider the plane containing M and orthogonal to P in this way. This plane is also a plane of symmetry for the plane P, as it defines two regions, one coming out of the screen and one going inside the screen, and these two parts are also infinite, uniformly charged, so E cannot have a component going inside the screen or outside the screen, so E should be again orthogonal to EX. So with these two symmetries, we know that E only follows the Z direction. But what about variables? If we do a translation along the x-axis or the y-axis, the charge distribution does not change, as we are assuming an infinite plane. Thus, the charge distribution does not depend on x or on y. Consequence is that the field E wouldn't depend on x or on y, neither. It would only depend maybe on z, if it depends. So with all the symmetries, we know that the plane only depends on z and is following the z direction. So we can for sure plot it like this. Once we are done with the symmetries, we can now use Gauss Theorem. So remember, Gauss Theorem tells us that the flux of E across a closed surface S is only equal to the charge contained inside S divided by epsilon 0. We just need an appropriate surface S, and an appropriate surface S should benefit from the symmetries of the field E, so that this computation would be easy. We know that E is dependent only on Z and is following the Z direction, so if we are at a fixed value of Z, the field vector is the same wherever we are. Here, also, from the fact that the plane is itself a symmetry plane for the charge distribution, we know that if we are on minus Z, we would have a symmetric value of the field. So any surface having a face on minus Z and plus Z would be an appropriate Gauss surface. Let's take, for example, a surface like this, having two faces symmetric. This face is on plus Z and this face is on minus Z. The other faces are orthogonal to the field, so the flux across them is 0. If we call this S1 and this S2, the area of S1 and S2 being the same, E is constant in S1, so the flux across S1 is constant and the surface vector is parallel to E. The same applying here. We'll have just 2 times E of Z with this symmetries, area of S1. And what's the charge inside our cube in red? The charge that the red cube would block inside it is its intersection with the infinite plane, which I will draw here in green. And this green part of the plane has also a surface equal to S1 and S2 with a density sigma. So it's simply sigma times S1 divided by the epsilon 0 of Gauss theorem. We can now simplify by S1 and conclude with the fact that E is not even dependent on Z and is simply equal to sigma over 2 times epsilon 0 and directed by the vector EZ. Of course, for the other parts of the plane, there should be a minus here. So I'll write plus or minus depending on the face where you are. So this is how we calculate relatively easily the field created by an infinite plane without doing any complicated double integral, just because we benefited from the symmetries and Gauss theorem.